Hello everyone, my name is Daria, and today I will present a detailed review of the research paper titled TROPICCAL, Multi-Perspective Trace Clustering for IoT-enhanced Processes, published in the journal Computers in Industry in 2026. The study was conducted by Yanis Bertrand, Johan de Wert, and Estefania Serral from Q11. This research is situated within the emerging field of IoT-enhanced process mining, which focuses on the integration of high-level business logic with low-level physical sensor data. As organizations increasingly adopt smart manufacturing technologies, the methodologies proposed by the authors become essential for understanding complex process variants influenced by environmental factors. To provide a clear roadmap for this presentation, the discussion is structured into several key sections. We will begin with the motivation behind this research and the limitations of previous models, specifically TROPIC. Then, we will examine the technical core of the TROPICCAL methodology, including the use of the de Moirol-Levenstein distance and context events for sensor data analysis. Following the methodology, we will outline the two-step clustering process and the specific hyperparameters used in the experiments. A significant portion of this task will focus on the new explainability features that allow the interpretation of resulting clusters. Finally, we will review a real-world case study in smart manufacturing and the feedback provided by domain experts. The authors identify a critical limitation in contemporary process mining technologies. Traditionally, these techniques focus almost exclusively on the control flow perspective, which records the sequence of discrete activities within an information system. However, in smart manufacturing, processes leverage Internet of Things technology to capture contextual data from the physical environment. The researchers argue that existing techniques often fail to capture the dynamic interplay between activity sequences and IoT readings. For instance, a standard model may identify a process deviation but fail to reveal that a specific sensor drift, such as a temperature spike or pressure drop, was the underlying trigger for that event. TROPICCAL was developed to address this gap by integrating control flow, trace attributes, and time series sensor data into a unified analytical framework. It is essential to understand the evolution of this research from the author's previous work. A model known as TROPIC, which stands for Trace Attributes, Control Flow plus IoT Clustering. While TROPIC represented a significant advancement in multi-perspective clustering, the authors acknowledged the two major limitations that hindered its practical application. First, TROPIC processed time series sensor data in a generic manner, ignoring the inherent complexity and specific patterns present in the data. Second, the model lacked a formal approach for explainability, providing no systematic way to justify the formation of specific clusters. The new methodology, TROPICCAL, or TROPIC Context and Explainability, addresses these flaws by incorporating expert knowledge through context events and introducing specialized explainability techniques. The first of the three perspectives in TROPICCAL is the control flow. To measure similarity between process distance instances, the authors utilize a distance-based approach employing the de Moirol-Levenstein distance. The DL distance is a string metric used to compute the edit distance between two sequences. It calculates the minimum number of single-character operations required to transform one sequence into another. As defined in the formula provided by researchers, the cardinality of A and B denote the lengths of strings A and B respectively. A sub I and B sub j represent the ith and jth characters of the strings. The term delta of A sub I and B sub j is the Kronecker delta function, which equals 1 if a sub I equals b sub j and equals 0 otherwise. The formula accounts for 4 operations: insertions, deletions, substitutions, and transpositions. The final term in the minimum function corresponds to transposition and is included only if I and j are greater than 1, and we observe that a sub I minus 1 equals to b sub j, while b sub j minus 1 equals a sub I. This allows the model to recognize when two activities have swapped order, a common occurrence in flexible manufacturing, without over-penalizing the distance between those traces. The primary innovation of TROPICCAL is the treatment of time series sensor data through the detection of context events. A context event marks a process significant happening detected in the time series sensor data, such as flow shifts or machine shocks. The researchers proposed two distinct methods for analyzing these event sequences. The first one, sequential ordering, utilizing the DL distance to compare the order of sensor events. This is applicable when a parameter follows a specific life cycle, such as an oven heating and cooling in a set order. The second one is frequency-based encoding. This method counts event occurrences regardless of their order, which is suitable for cumulative impacts, such as the total number of physical shocks a product receives during transport. The second perspective involves trace attributes, which is numerical or categorical features associated with a process instance, such as solvent type or tank ID. For this perspective, the researchers utilize a k-means algorithm. TROPICCAL follows a two-step clustering protocol. In the first step, each of the three perspectives is clustered independently to determine the optimal number of clusters. The authors employ the elbow method. Once independent clusters are established, the distance to each centroid are calculated. These distances are then weighted and normalized to serve as features for the final stage, multi-perspective clustering. To ensure a rigorous comparison, the authors detailed their experimental setup in table, which is a summary of hyperparameters used for each multi-perspective clustering technique. One critical hyperparameter is the number of multi-perspective clusters, determined via the elbow method. For TROPICCAL, the researchers identified 6 clusters, whereas the baseline weighted sum approach utilizes 3. This indicates that TROPICCAL captured a higher granularity of process variance. Another key detail is the scaling method. While TROPIC used standardization, the authors found that normalization performed better for TROPICCAL, yielding superior internal validation metrics in this use case. This highlights that the effectiveness of multi-perspective models is sensitive to data preprocessing choices. To ensure the model is not a black box, the authors introduced 2 levels of explainability. The first level involves global clustering comparison metrics. Metrics such as the adjusted trend index and entropy are used to evaluate the similarity between partitions. By comparing the final multi-perspective clustering against each single perspective result, the authors can mathematically demonstrate which perspective, activity, or sensor context dominated the formation of a specific group. The second level is permutation feature importance. This technique calculates the contribution of individual features to the cluster labels. By randomly permuting a feature's values and observing the impact on the model, the researchers identify exactly which sensor drift A specific activity defines a process variant. The authors validated TROPICCAL using a case study at a chemical engineering company. The production process involves 4 stages: material preparation, mixing, filtration, and bottling. If quality is insufficient after filtering, an adjustment loop is triggered. In the researcher's visualizations, a color-coded system is employed. So the orange for preparation, green for mixing, light blue for filtration, red for adjustments, and dark blue for bottling. The example pump flow data provided the environmental context for the analysis. Looking at the results in figures in the paper, we see the analytical depth of TROPICCAL. The figure illustrates the control flow for cluster 1, while the figure 10 shows its corresponding context event sequences. The researchers found that some batches follow similar activity paths but belong to different clusters due to sensor stability. For instance, cluster 2 exhibits a more stable flow compared to cluster 1, despite having similar control flow sequences. Experts confirmed that TROPICCAL identified subtle differences, like specific flow drifts, that baseline methods fail to distinguish. And they mentioned, the higher granularity and better sensor impact analysis. In conclusion, the researchers have demonstrated that integrating IoT data as context events significantly enhances the depth of trace clustering. By utilizing advanced metrics like the Merau-Levenstein distance and providing a comprehensive explainability framework, TROPICCAL offers a data-driven understanding of complex manufacturing operations. The authors suggest that future research will focus on generalizing the model to n-arbitrary perspectives and incorporating event-level time series data. This concludes the review of the TROPICCAL methodology and the end of my presentation. Thank you so much for your attention.